oversimplify the CS representation, and they keep the CS contribution static, and this phenomena is ignored in the model. So that would we previously have proved that this would cause some bias in the forecast skill, and what's more, they also use a constant CS thickness and snow height. That means they treat the CS thickness and snow height as a 1 meter or 2 meter constant slope during the model running, and not the realistic CS thickness or the realistic snow height or simulated by the model. But yeah, that would also cause some problems, and many global numerical weather prediction centers like the ECMWF, UK Met Office, they have realized these problems, and they are developing the fully coupled numerical weather prediction model with a complicated CS model like the SAS6 or the LIM3, and to overcome these problems. But for Antarctic optimized model, Antarctic optimized numerical weather prediction model, they still use a very simple CS representation. They don't have a complex CS representation. So the influence of coupling a complex CS model into the numerical weather prediction in Antarctic is unknown. And so what we are doing here is to investigating the influence of that. The model we used for simulation here is a polar-WRF model. Polar-WRF is a polar optimized WRF model. A WRF model is a weather and forecasting model developed by NCAR. And we used the polar-WRF model to do some simulation for the year 2018. And the left figure shows our simulation domain that covers the whole Antarctic CS region with a 30 kilometer resolution. And we use Aero 5 as our initial and boundary condition that force that the boundary, and for obtain a realistic surface condition, surface boundary, we also use a CS contribution from we also including the CS contribution from an SIDC climate data record CS contribution into the model. Okay, and the first thing we need to do is to ensure our model is accurate enough for this research. So as we interested with the CS region, so here we use RV snow buoy that measures the near surface temperature, namely the 1.5 meter air temperature, to do a validation. And in 2018, there are 7 snow buoys deployed at the Weather Sea, and one the blue line here is a one snow buoy deployed as a multi-year ice, and other 5 snow buoy deployed as first year ice, and another one deployed as a ice shelf for validated its 6 snow buoys. We first validated the Aero 5 reanalysis use RV snow buoy because Aero 5 is used for initial and boundary condition for our model. So ensure the boundary condition is accurate is important, and we can see the left panel that use Aero 5 versus the snow buoy. We found the correlation is pretty high. The correlation is 0.97. That's pretty high because the snow buoy measured 1.5 meter surface temperature has been assimilated into the Aero 5 model. So our initial condition and boundary condition, initial boundary condition for our model is pretty accurate. So here we validated the model. We set up a series of model runs every 10 days for the whole year of 2018, and we run the model every three times of the month that cover all phases of the CS advance and CS retreat within the calendar year to give a comprehensive evaluating of the model. And we do an average for every 2-day forecast, 2 forecast days. So we can say that this is the first 2-day forecast, and this is the last 2-day forecast for the 10-day forecast. And with the forecast period increase and the bias is increase and the correlation is decreased. But for the first 2 days, the correlation is pretty high and the bias is pretty low. So that means the first 2 days, Powerwolf did very well, and we also did individual test for each buoy site, and we found the buoy has a very good correlation, with the Powerwolf simulated 2-meter temperature, except at a buoy site at the ice shelf. But we in this research we mainly interested with CS region. So for this 24 hours forecast, the model at CS region is pretty accurate. So that means the model is accurate enough for the temperature investigation over the CS. But we know the seven slow buoy are only available at the Weddell Sea, which cannot provide a special distribution of temperature variability over the CS. So here we implement another ice surface temperature data from a satellite-derived ice surface temperature from Moody's, which is used to evaluate the skin temperature simulated by the Powerwolf over the CS. And the left figure shows the skin surface temperature simulated by the Moody's, measured by the Moody's. The data availability, the Moody's ice surface temperature is pretty good available at the CS region, and this is the mean status of the ice surface temperature measured by the Moody's. And here we should say that previous we found the Euro 5, the real analysis like Euro 5, Euro Interior, and also our Powerwolf model simulated surface skin temperature have a considerable warm bias over the CS. That is caused by the mismatch of cloud cover between the Moody's and the model simulation, like Powerwolf or like a Euro 5 model. So here, to avoid this warm bias, we only consider the pixel that are cloud-free in both Powerwolf and Moody's. So we reduce the data point to avoid this warm bias. So here, then we set up several experiments to investigate the temperature sensitivity to the CS thickness and snow depths. We set up a series of Powerwolf simulation with a different prescribed sighting of CS thickness from 0.5 meter to 3.5 meter. And we also investigating the sensitivity of snow depth to the ice surface temperature. So we set up the CS thickness to be a 2-meter constant, and we set up the snow depth from 2 centimeter to 30 centimeter. So we also interested with the the influence of ocean CS model simulated CS thickness on the ice surface temperature prediction. So here we include geomass access OM2 simulated CS thickness into the model, as well as their simulated snow depth into the model, and see their influence. and we have said the first 48 hours is pretty high accurate. So the first 24 hours are discarded as the span of time, and we set up a lot of runs in 2018, initiated every day, and only the 24 hours is combined to a completed year run for the analysis, and we against the model. We against the Moody's measure as the temperature. So this figure shows the as the temperature sensitivity to the CS thickness from left panel of the figure to the right panel. The CS thickness sighting is increased from 0.5 meter to 3.5 meter, and with the increase of CS thickness, we found the estimated temperature simulation is the estimated temperature bias versus Moody's estimated temperature is a decrease. It turns from warm bias to almost a cold bias. But interesting that as the Western models say, they are still a warm bias even at the CS thickness with 3.5 meter and slope height is 5 centimeter. That means at this region, 3.5 meter CS thickness and 5 centimeters slope height is still too thin to block the ocean overheating the surface. For the and this figure, the bottom figure shows the annual variability of the as surface temperature by sensitivity, and we found in the winter. In the winter, the sensitivity is much higher than the sensitivity in the winter. It's because in the winter, the temperature difference between the atmosphere and the ocean is much larger than the summer. So that causes the ice conduction in the winter is pretty larger than in the summer. And similar sensitivity for the slow depth, that's the warm bias. A warm ice surface temperature bias is decreasing. It turns to a cold ice surface temperature bias with slow depth increase from 2 centimeter to 30 centimeter. As well as the annual variability is high sensitivity in the winter than in the summer. Then we are discussing we are interested with the influence of ocean CS model simulated CS thickness and slow height on the ice surface temperature estimation. And the left right two panel is a polar wolf simulation only including the CS thickness from ocean CS model simulation. The slow depths are still simulated by the polar wolf itself, and the polar wolf we set up 5 centimeter for the lower bound, and the polar wolf is 5 minutes. It's increase or decrease based on the precipitation or the melting, but it's mainly depends on the it's mainly but the influence is very small. We can nearly treat this one as the 5 centimeter constant. So we can see when we only including the CS thickness from ocean CS model simulated that the model at most region shows shows a warm bias, but when we including access OM to simulated slow depths and access simulated slow depths into the models. The warm bias turns to the cold bias. And for the annual variability, we added a reference for the CS thickness and the simulation with a constant slab CS thickness, and we found the model doesn't have a good outcome when when including the ocean CS model simulated CS thickness and snow depth. And we found sometimes they show the cold bias, they show the warm bias, and sometimes they show the cold bias. And we use CS thickness and snow depth to investigate the influence. We including here is a satellite derived CS thickness, and the middle one is access OM2 simulated CS thickness and geomass CS thickness. We found that access OM2 have a better simulation of the CS thickness than geomass, and also for the access for the snow depth, they all have a better simulation. So that cause at some regions that they have a good forecast skills and a constant slope. And we found geomass when we included geomass simulated CS thickness snow height into the model. We found there is a cold bias, and why this cold bias happen is because the geomass simulated snow height is too high, it's much higher than the observation, and that's cause the cold bias here. And for the warm bias in the winter, so for the warm bias in the summer here, caused by the Powerwolf simulation, including the access OM2 simulated snow CS thickness and snow height. Here it's because the access OM2 simulated CS concentration in summer is much lower than the observation SITC. This is mainly because the access OM2 doesn't simulate the satellite derived CS concentration, while the geomass simulated the SITC CS concentration. So here we give a conclusion here that including model simulated CS thickness and snow depth at this stage into the Powerwolf model did not produce a noticeable improvement in the surface temperature forecast scale. Okay, and we found that CS thickness and snow height has a considerable influence on the surface temperature, but the combination effects of varying CS thickness and snow height on the surface temperature still require further investigation. So the last experiment here, we aim to find the optimized parameterization of the CS thickness and snow height for accurate simulating the surface temperature in the Powerwolf model. So in this experiment, we set up a series of the tests that use a different combination of constant CS thickness and snow height prescription just shown here. We run this model for the 2018 July, and we also we got this result and versus the surface temperature simulation. We versus the surface temperature simulation with modest surface temperature, and we got the domain average bias at each test. And we found the larger panel is a sub-panel. The larger panel is for the the dome average for the whole Antarctic. And we found there are several local minima in the whole heat maps we found, for example, 5 centimeters snow depth and 2.5 meter CS thickness, and the 10 centimeter snow height and 1 meter CS thickness show a good reasonable choice. And we also found when we do average for different regions, that the results is pretty different. So the individual optimized CS thickness snow height parameterization for different CS region is important. So okay, we got a conclusion that at surface time we investigating the the ice surface temperature sensitivity to the sea ice thickness. And we also found at this stage, the model simulated sea ice, including the model simulated sea ice thickness and slow height into the Polar Wolf model cannot produce very good improvements due to the model have the shortage. And we also give a better representation scheme for Polar Wolf in different areas of Antarctic. And yeah, and that's all today. Thanks.
Thank you, Wang. That was very interesting. Any questions from the audience here? Rob.
Rob Massam, thank you very much indeed, Wang. I was just wondering about, do you assume that the snow that falls from the ERA model all accumulates? Is that an assumption in your study, please?
Yeah, in for our simulation here, we truly we investigate. Sorry, maybe here we investigating the influence of sea ice thickness sensitivity. We allow the store depth simulated by the Polar Wolf itself, and the Polar Wolf is accumulating or melting based on the Polar Wolf itself. But we found for the short term weather forecasting, I mean the 24 hours, the accumulating or the melting is really small, that can be neglected, that can be neglected and can be treated as a constant value for 5 centimeter.
Yeah, thank you, Wang. The reason I asked is that typically when snow falls on Antarctic sea ice, it's under windy conditions, and a lot of the snow blows across the surface, so it's redistributed. And I think there have been some studies that suggest that up to 50% of the snow may be lost into leads. So there may be a strong discrepancy between actual snowfall and what accumulates on the surface.
Yes, sure. But for our NWP time period, numerical weather predictions, short-term NWP, 24 hours maybe at least for our simulated period 2018, the accumulation or the melting is pretty small, so that nearly doesn't influence the research results. Yeah. But maybe for long-term simulation, the influence is more significant.
I have one more quick question for Wang. Okay, I've got one for you, Wang. Would you mind just stopping sharing just while Nathan's setting up, and I can ask you a quick question? It seems like most of your bias is largest in the summertime. Did you try, I know the answer to this because I'm your supervisor, did you try modifying the albedo, because this would have the largest effects in the summertime? What do you think?
I think maybe the albedo is important in summertime. It's important to adjustments in our future research. But for the last experiments for the June, the Antarctic winter maybe is not very important to adjustment.